In this video, we're going to look at how to use the various properties of exponentials and logarithms that we've developed over the past few days in order to solve equations involving exponentials and logarithms. So why don't you pause, copy down this first panel, which should all be review, and then press play. All right, so this panel is sort of reminding you of the various interesting properties of exponentials and logarithms that we've developed, right? So first off, the bases that we're going to be considering, the values of b, they're always going to be greater than 0, and b equals 1 is sort of silly, although all the statements are certainly true for b equals 1. But okay, so b raised to the 0 power is 1. If I have b to the a times b to the c, I combine the powers into a single exponential, b to the a plus c. Division works similarly, but with subtraction. And then if I have an exponential function raised to a power, I can multiply the two powers together to combine them, right? Now, exponentials and logarithmics are linked, right? So a log base b of a equaling c, that is equivalent to saying b to the c equals a. And I could read that line backwards. B to the c equals a is equivalent to saying the log base b of a equals c, right? Then I've got some properties for logarithms. Since b to the first equals b, the log base b of b is 1. Since b to the 0 equals 1, the log base b of 1 is equal to 0. And then the next two are just explaining that b to the x and log base b of x are inverse functions of each other. So if I take the log base b of an exponential function, I just get back x. And if I take an exponential function with the power being log base b of x, I just get back x. So the logarithm undoes the exponential, and the exponential undoes the logarithm. So that's the inverse relationship between the two functions. And then most recently, we picked up these handy algebraic properties. The log base b of a product can be written as the sum of two logs, or the sum of two logs can be combined into a single log. The log base b of a quotient can be split apart into the difference of two logs, or the difference of two logs could be combined into a single log with a quotient inside. And then the log base b of m to the n can come down in front, and I'll have the log base b of m. Or I can bring the n up to the power of m if I wish to. Okay, so we've sort of covered all those before. Now we're going to start to use them in the 6 problems I'm going to work through in this video. All right, so why don't you pause, copy this down, then press play. All right, so we are going to focus on 3 main types of problems in this section. And here's the first type. This is the type where we have an equation with exponentials in it, but the exponentials all have the same base, all right? And the solution idea is going to be due to the fact that the graph of b to the x passes the horizontal line test. So like the graph of b to the x is either that or it's that. It passes the horizontal line test, which among other things means that if b to 1 power is equal to b to another power, then the two powers had to be the same. There is not 2 different values of a and c where they have the same output. Otherwise, we would have failed the horizontal line test. So if I ever grind it down, an equation down to a situation like this, I can automatically just focus on the powers, right? All right, so let's look at this guy. I've got 3 to the 4x minus 7 is equal to 1/3 times 9 to the x. Now, those don't look like they have the same common base, but I can transform them so they do, because 9 can be written in terms of a power of 3. So let me do that. So the left side, I'm just going to leave it alone as 3 to the 4x minus 7. There's my 1/3. And 9 is the same as 3 squared. Might need a bail on that blue. Okay, so 9 is the same as 3, squared, okay? All right, now from the earlier panel, I know how to combine 3 squared raised to the x power. That would be 3 to the 2x. So I'd have 3 to the 4x minus 7 equals 1/3 times 3 to the 2x, okay? All right, Now 3 to the 2x over 3 is 3 to the 2x divided by 3 to the first, right? So I should be able to combine those two by subtracting. So getting the new power of 2x minus 1. Also based on the properties in the panel over there. So I would have 3 to the 4x minus 7 equals 3 to the 2x minus 1. All right, well, now I'm in a situation where I have b to 1 power equals b to another power. So by this one-to-one nature, or this passing the horizontal line test nature of the exponential function, I can just say the two powers have to be equal. And now I'm back into happy algebra land with linear functions. So let me subtract the 2x over to there. So 2x minus 7 equals negative 1. I could add the 7 to the other side. So that would give me 2x equals, if I add 7, that give me 2x equals 6. So I'd have x equals 3. All right. Okay, so made both exponentials the same base, and then just fixated by setting the powers equal to each other. All right, well, let's play a similar game over here. I've got 8 to the x equals 16 to the x plus 5, trying to solve for x. 8 and 16 are not the same number, but I could transform each of them into a common base. Both 8 and 16 are powers of 2. So I could write 8 as 2 cubed. I could write 16 as 2 to the 4th. And then using the properties of exponents, 2 cubed to the power of x is 2 to the 3 times x. And 2 to the 4th to the x plus 5th is 4 times x plus 5 is my new power. Okay. And now they're both powers, or sorry, they're both exponentials with base 2. So I can just set the powers equal to each other. So I could set 3x equal to 4 times x plus 5. And again, this is now happy algebra land. So I've got 3x equals, if I run the 4 through, I've got a 4x plus 5. I think I could subtract a 3x, so I'd have an x plus 5, and then subtract the 5 over, so I get x equals negative 5. Okay. All right, so convert to a common base for the exponential function, set the powers equal. All right, so the second type of problem then is, what if I can't do the technique over there? What if I can't get both of the exponentials to have the same base? Then what? Okay, so why don't you pause, copy these two down, and then I'll crank forward. All right, so in example 3 here, I've got a base of 5 and a base of 4, and I can't think of anything that I can make both of those common powers of, right? So I feel like I might be kind of hosed here. And the problem is the unknowns are up in the powers. So we're going to use one of the properties of logarithms to try and, push us through to the finish line here. So take whatever log base you like that a calculator can handle, which basically means either the natural log or the common log. It doesn't matter which one you use. I'm going to just pick the natural log because it's only 2 letters to write down and I'm lazy, all right? So what I am going to do is I'm going to take the natural log of both sides. Whatever I do to one side, I must do to the other. So I could take the natural log of 5 to the x plus 2, and that would equal the natural log of 4 to the x, okay? All right, it looks like I've made it worse. But one of the properties of log says I can take the power from inside the log and drag it out to the front. So I'm going to do that on both of these. So I'm going to get an x plus 2 times the natural log of 5 equals an x, the x comes down in front, times the natural log of 4. All right? Now, this is a much nicer algebraic expression. The natural log of 4 is just some number. The natural log of 5 is just some number. So this is pretty much a linear kind of equation that I need to solve. So I'm going to solve it like that. I'm going to run the number, the natural log of 5, through the parentheses. So I'm going to have the, I'll just write it this way. I'm going to have x times the natural log of 5 plus 2 times the natural log of 5 equals x times the natural log of 4. All right? Okay, now I'm going to get everything involving an x on the left side and everything without an x on the right side. So I'm going to subtract the 2 times ln of 5 to the right, and I'm going to subtract the x ln of 4 to the left. So I've got x times ln of 5 minus x times ln of 4. Okay. All right. Since I have everything involving an x on the left, I can factor my x to the front. So I have x ln of 5 minus ln of 4 equals -2 ln of 5. And if I'm trying to solve for x, I can now take this number, ln 5 minus ln 4, and divide it underneath the other side. And that would get me x all by myself. So I've got the -2 ln 5 all over ln of 5 minus ln of 4. And that is a number my calculator can tell me, all right? Pretty quickly. Poof, magic. All right, so I just grabbed my calculator and I typed in -2 ln of 5 divided by parentheses ln 5 minus ln 4 and parentheses. And I got x was about -14.425. Okay, all right, so this is one way to do it. The natural log or the common log or any log for that matter, but one our calculator can handle. If I have a natural log, I can drag those powers down out of the power onto the main line where my algebra skills can handle it. All right, similar problem here. I've got 100 equals 20e to the 2t, and I don't know how to write 100 as a e to a power, right? So how do I solve something like this? Well, I'm going to first try and isolate the exponential part of this expression. So I'm going to take my 20 and divide it to the other side. So I got 100 divided by 20 equals e to the 2t. Cool. Well, 100 divided by 20 is just a 5. So I have 5 equals e to the 2t. I'm trying to solve for t. It's stuck up in the power. So I'm going to do the exact same trick. I'm going to take the natural log of both sides. And the natural log is actually the best choice here because I know the natural log and e kind of undo each other. So I'm going to take the natural log of both sides. So natural log of 5 equals the natural log of e to the 2t. Now, natural log of 5, it's a number. My calculator can give me a good approximation of it, so I'm not worried about that. And on the left, sorry, on the right, a couple of different ways I could do it, but in particular, I can say the 2t, the power can come down in front, and I've got the natural log of e. Okay? All right, well, if I circle up to here, got the natural log of 5. The natural log of e is just 1. This is log base b of b, right? So we know that's just a 1. So I have a 2t times a 1. And if I wish to solve for t, I can divide both sides by 2. And if I wish to actually get a decimal approximation for that, I can say ln of 5 divided by 2. I'm getting approximately, since I'm cutting off some decimals, 0.8047, ... Okay. All right, so I can use logs to drag powers down in front. And as long as I take the log of both sides, everything, mathematically speaking, stays balanced. All right, so last two problems and the third type of problem we're going to encounter. We're going to use some of the log properties to simplify the problem in order to solve the equation. Okay, so why don't you pause, copy these down, and then I'll work through them. All right, so here I've got the sum of two logs is equal to 3, and I know the two logs have the same base, and that's awesome. So what I could do is I could combine these two logs into a single logarithm, right? So this would become the log base 2 of, if I've got the addition of two logs, I can combine them by saying this is 5 times 3x minus 5. All right, the log of m times n was the log of m plus the log of n, all right? So that's what I just did there. And I've got a 3 on the other side, no worries, all right? So now I have a single logarithm equal to a number, and I can just flip this to its exponential form. So that would tell me that 2 cubed is equal to this thing, 5 times 3x minus 5. All right? All right, well, now we're just in happy algebra land. 2 cubed is 8. Running the 5 through gives me a 15x minus 25. And I could add the 25 to the other side, so I think that would give me a 33 over there is equal to 15x. And then if I like, I could divide both sides by 15 to get x all by itself. So that would give me a 33 over a 15. All right. And then last example, I've got 2 natural logs, but again, same base, equal to each other, right? So there's a few different ways I could do this, but let me just stick with the properties of logarithms like I illustrated in example 5. I could get both of these natural logs on one side together. So let me just subtract this natural log over to the left. So that would give me the ln of x squared minus the ln of 2x plus 3. And I now have a 0 on the right. Well, if I have the difference of 2 logs with the same base, I could combine them into a single log like I did up here. But this time, it would be x squared divided by 2x plus 3 equals 0, right? So the log of a quotient is the difference of 2 logs. Now I'm going to flip it to exponential form. And we remember that the natural log has a base of e. So the exponential form would be e to the 0 equals x squared over 2x plus 3. Right? Okay, well, e to the 0 is just 1. So I have x squared over 2x plus 3 equals 1. Let me go up over here now. I don't like quotients with the variable I'm trying to solve for. So I'm going to take my 2x plus 3 and multiply it to the other side. So 2x plus 3 times 1 is just going to give me a 2x plus 3 on the left and an x squared on the right. And I'm feeling a little bit better about this because now if I get the 2x and the 3 over to the left, I'd have a 0, sorry, over to the right, I'd have a 0 on the left, and I would subtract the 2x and I would subtract the 3. And x squared minus 2x minus 3, either I could now use the quadratic formula on this, or I could see if it factors. And I think it does factor into x minus 3 and x plus 1. Right? And then I get the answers of x equals 3 and negative 1. Okay. All right. So those are my 2 solutions. And I'm all fine and dandy. Okay. I might just be slightly nervous about whether these both work. I never took a square root, but yeah, I think these both work. So if I plug in x equals negative 1, I get a negative 2 plus 3. I get the natural log of 1. Natural logs can handle 1. Negative 1 over here is a positive 1. I was worried that this solution with a negative sign would give me the natural log of negative numbers, which is undefined, right? But I could check, and if I plug either negative 1 in or 3, the natural log can handle what results. All right, shut up, Axel.